So today we're going to finish up section 4.5, and we're going to keep looking at wave structures, and we're going to look at graphing techniques. I'm going to teach you some processes to follow when you're trying to graph these waves in ALEKS, but then I also want to go over how do you graph these waves by hand. So there's definitely a technique to it that cuts the work way, way down. And then we're also going to look at, can we read the description of a wave and come up with the correct equation? And then can we look at a graph of a wave and come up with the correct conclusion? So all of the trig functions are graphed on your graphs you should know sheet. I told you guys the bottom graphs we get to at the end. So those are on your handout that I gave out to you guys earlier in the semester. So the first thing that I want to do is I want to revisit the two waves we looked at the end of class on Wednesday. So the first one we looked at was this. And on the second one, we saw that if we actually wanted to be able to see the phase shift in the wave, we had to rewrite it by factoring the 8 out. So one of the things you want to make sure that you can do when you're looking at a wave is you want to make sure if we ask you to find the domain and range of that wave, right? So it's a little different with trig functions because you need to know inside and out what the base equation looks like, so then you can easily make adjustments. But there aren't a lot of algebra ways to do this, okay? So for sine, that first wave, we said, well, that's just a regular old sine wave that was shifted 5 pi over 9 to the left, all right? So on a standard sine wave, it's a wave that goes forever in both directions. So the domain of all cosine and sine waves is always going to be all reals. Because anything you do to the inside of the wave, shift it left or right, it's not going to have any effect on its domain. So right out of the gate, we actually know that the domain of these waves is all reals. What can change are the ranges, right? And so if we shift it up and down and move it around, and so there's some techniques for that. So remember that D in the equation is telling you where the center of the wave is. And then the amplitude is telling you how far from the center each of those functions travel. So if we look at the first one, well, there is no D on the outside of the equation. The center of that wave is at 0. So I can see also that the amplitude of that wave is 1. So if I go 1 unit up from 0, we know the wave never goes above 1. And if I go 1 unit down from 0, I know the wave never goes below -1. So the range of this first equation, right, is -1 to 1 included, because we're talking about the top and bottom, the max and the min, are points on the graph. So we always include those values, right? For the next one, what happened was we shifted the wave down 3 units. So now the center of the wave is at -3, right? But the amplitude is 7. So the maximum value of this wave is you start at its center and you add the amplitude and you get that the peak is now at 4. The minimum value of the wave, you start at its center and you count down 7 units, and we see that the bottom of the wave is at -10. So the range of this wave, is -10 to 4, and they're still included. So if you understand how waves work, these are very, very quick problems for you to do. So A and D are always going to talk about the vertical part of the wave, right? And the inside's just going to be all reals. All right, let's look at another one. So I mentioned on Wednesday that it is absolutely possible for you to have a negative sign in front of one of these waves. But the way that you want to read that is actually -1 times 1/6. So if we ask you for the amplitude of this wave, right, the correct answer is 1/6. You would never give a negative amplitude because it's just the distance that the wave goes from its center line, right? The -1 means we flipped it over the x-axis. So a cosine wave normally starts at its peak, but what will happen is if we flip the wave upside down, this cosine wave starts at its trough, right? So it's all that -1 is doing, right? The frequency of the wave is 4/5. So that means 4/5 of the wave has gone by every 2 pi, because we're always comparing it to the original standard wave, right? If you want to know the time period of this wave, we said, well, that we find by doing 2 pi divided by the frequency. So that would give you 10 pi over 4, which reduces to 5 pi over 3. So it takes 5 pi over 3 for one complete wavelength to go by. 5 pi over 2. Thank you. Math is hard today, guys. So then there's no phase shift here because nothing's being added or subtracted on the inside of the function. So we're not shifting the wave left or right, but we can see that our D value, or the center line of the wave, has been moved up to 3. So if I want to find the domain and range of this wave, well, the domain is all reals. But to get the range, right, the minimum value is the center point, right, minus the amplitude of 1/6, and you get 17 over 6. The maximum of the wave is at the center line plus 1/6, and you get 19 over 6. So this range is 17 over 6 to 19 over 6. So a lot of times when they start asking about domain and range, they'll slowly build up the problem by changing things about it. So you might do 3 or 4 in a row where the center line is 0, and then students kind of fall into the trap that the range is always the amplitude to the amplitude negative positive. And that's true until you have a vertical shift. And so really what you want to think about in your mind is where's the center of the wave and count it for there. So if the center is 0, it's negative A to A, but if the center is non-zero, you have to count from that point up or count from that point down. But it's a very easy calculation to do if you understand the structure. All right, so let's talk about graphing waves, all right? So if you want to graph waves, all right, there's 2 ways you're going to do this. In ALEKS, the way you do it is you have to give them 5 points on the wave, and then you'll hit the graph button and it's going to connect the 5 points and draw the wave for you, all right? But there's a strategy to it. You really want to give them 5 very specific points. So if you notice when we drew our sine wave on Wednesday, I did it by going around the unit circle, and the points that it gave me back on the wave were the middle, the top, the middle, the bottom, the middle again, okay? So we found the midpoint, the top, the midpoint, the bottom, the midpoint. And those are the points you want to report in, right? If you are doing it correctly, if there's a strategy to it, you shouldn't have to do a ton of calculations, and you should never be plugging values into the wave equation and solving for y. That is an extremely inefficient way. So when we graph logs, I told you guys, well, there were 2 mathematical properties of logs that you should take advantage of when you're trying to find points, right? Log base anything of 1 was 0, and log base anything of its own base was 1. So we strategically picked values of x to turn the expression inside the wave either into 1 or its own base, and that made it easy to find points, right? So we're going to do something similar here. So let's look at an equation, and let's see how to find these points, all right? So if I let f of x be 3 sine of 13x. It's a sine wave, and so since sine usually starts at its midpoint, if I draw one period of the wave, it's going to look like this. And these are the 5 points that I want to find and put into ALEKS. So the first thing that I see is that there's no vertical shift here. Our center line is 0. So that means that the x-axis, right, is running right across here. So the y value of all of the midpoints are 0. If I look at the amplitude of the wave, well, the maximum of the wave is just the center line plus 3. So that means the y-coordinate of this point here is 3, and the y-coordinate of this point down here is -3. So the y values should always be really, really obvious. Then what you're doing is you're really being asked, how should you index the x scale? So that way you're just finding these x coordinates. And there's kind of a trick to that. So the first thing you have to worry about was there a phase shift in your wave? And the answer here is no. We didn't shift it left or right. So this sine wave starts where all normal sine wave starts, and that's at the origin. So that means, right, this is actually my y-axis. If there was a phase shift, like let's say we were looking back at that first equation where it was x plus 5 pi over 9, well, I would just take the origin point and I would shift it left to -5 pi over 9, right? So now the question is, what are these tick marks? So one of the nice properties about waves are, if you look at any portion of the wave, then that same portion of the total time period has gone by. So this point right here splits the wave in half. So if this thing has a period of whatever it's going to be, we would say that half the time has gone by to get here, right? This point right here splits that half in half. So what you want to do when you're working with these waves is you're literally looking at every fourth of the wave. That's what those points represent. It takes 1/4 of the time to get to the top. It takes another fourth of the time to get to the middle, another fourth to get to the bottom, and then another fourth to get back to the middle, all right? So if we can find the total time period, we can easily find these x values. So the frequency of the wave is 13. That means 13 of these go by every 2 pi, all right? So if we want the time period, we'd say, well, that's 2 pi over 13. So that's the total amount of time it takes for that wave to go by, right? So then what you're going to do, and it's always going to be a fourth, you're going to multiply your time period by 1/4, and that gives you the increments all the way across. So if we multiply 1/4 times 2 pi over 13, this simplifies into pi over 26. So since we're starting from 0, it's really easy to count across. So we go from 0 to pi over 26, right? Then we go another pi over 26, so that's 2 pi over 26. And then we're at 3 pi over 26 and 4 pi over 26. So we went 1, 2, 3, 4 across. Some of those fractions reduce, but don't worry about that. You don't have to reduce them. ALEKS doesn't care, right? So these are the 5 points you would type into ALEKS and then hit the button and it would graph your wave, right? Now, this is a little bit deceptive because the ALEKS graphs are always going to size themselves in such a way where the x scale looks convenient and the graph comes out nice and pretty. If you're drawing the graph by hand, right, one of the big mistakes that students make is the traditional way of graphing is you draw the x-y axis, then you label some increments and you start graphing. But that's going to actually cause a lot of problems with waves because if you don't know what the time period of the wave is, you could literally run out of paper before you can draw one complete wave, right? Or in a wave like this where the frequency is 13, if you labeled it from 0 to 2 pi, you'd have 13 of those guys go across, and then it's too tiny and you can't see what's happening. So what we do on graphs like this, if you're drawing by hand, is exactly what I just did for you. I drew the wave, and then I labeled everything around it. So it doesn't matter, your scale is now auto-zoomed, it looks like a nice wave. So start with the general shape of the graph, then find the numerical values and fill them in as you go, and then when you draw your XY axis in the appropriate place, you're done. So you almost like draw it in reverse when we're drawing it by hand, so that way we can actually see it. If you ever used a TI calculator, and maybe in high school when you were learning waves and trig, right, you would try to graph them, and if you just left the calculator in the standard -10 to 10 viewing angle, those waves could look really weird and crazy. But if you hit zoom trig, what zoom trig did for you is all it did was adjust the Y scale and adjust the X scale by the time period so you could see a nice fluid wave-like motion, right? So it adjusts the Y by the amplitude and that. So, you know, that's how you should be drawing these graphs. If we provide a graph for you to draw it on, we may or may not label the scale, right? So that's why you want to find your points, plot those, and you can scale it any way you want. If we do give you a scale to use, your wave should fit, but like I think one time I did one on a quiz or a test where I made the period of the wave 2 pi. The period of the wave was 4 pi, and I did the scale from -2 pi to +2 pi, so you would have only gotten one big wavelength across that graph. And it just freaked people out for, I don't know why, but I was like, well, if the period is 4 pi, it should make sense it took 4 pi to create the wavelength. So just practice with these. It's a good idea even when you're doing it in ALEKS to sketch and write it in, and then that way if you have to do it by hand, you're getting a little bit of extra practice. All right, so does this make sense? Because my last class had a lot of confusion about the 1/4. It's always going to be a fourth. You're always breaking the time period into fourths. And if you think about how we did it around the unit circle, I was going 1/4 of the way around the circle to grab each of those points and doing it. So that's why it was giving us 1/4 of the wave, 1/4 of the wave, 1/4 of the wave, 1/4 of the wave, right? Now, by this same token, if I randomly grabbed 1/3 of a wavelength, well, then you would divide the time period into thirds, and that would tell you how long it took. So whatever portion of the wave you grab, the portion of the time period matches that. All right, but when we're graphing, we're always going to split it into fourths because those are the 5 points that I want. All right, let's look at another one. So we've got -5 times cosine of x over 6. So the amplitude of this wave is just 5, but the -1 means we flipped it upside down. So if I wanted to draw a normal cosine wave, right, there's no shift here, I would normally start at its peak, but because we flipped the wave upside down, if I draw the first wavelength, right, off 0, I'm really going right from here to here. So since there is no vertical shift, we know the center of this wave is the x-axis, and this is going to be the y-axis. So normally cosine would start at the top, right, but we flipped it upside down, so we have to draw it this way. So now the 5 points that I'm supposed to generate are this one, this one, this one, and this one. So the bottom of the wave is going to be at -5. The top of the wave is going to be at 5. So I just need to figure out how to count my x scale. So the frequency of our wave is 1/6. So that means if I just read the x scale to all the way to 2 pi, only 1/6 of the wave has gone by, right? So you don't even get a complete wavelength in 2 pi. So if we calculate the time period, That's 2 pi divided by 1/6, which works out to be 12 pi. So I already know that that point on my scale is 12 pi. That's how long it takes for the whole wave to go by. If I want to chop this into fourths, this actually works out quite nicely for us. 1/4 times 12 pi is just 3 pi. So this means every fourth of this wave, 3 pi has gone by. So there's 0, there's 3 pi, there's 6 pi, there's 9 pi, and then we end up at 12 pi, just like we wanted. 3, 6, 9, 12, right? So this means the 5 points that I would give Alex, right, are 0, 0, or sorry, 0, negative 5, 3 pi, comma 0, 6 pi, positive 5, 9 pi, comma 0, and 12 pi, negative 5. So this is how you're supposed to do these problems. It's not trying to pick x's and plugging them in and getting these points. And they're going to ask you in questions things like, what is the coordinate point for the first maximum you see after 0, right? So once you've split this up, we're like, oh, well, that's 6 pi 5, right? They could ask you, where's the first middle, point when the graph is on its way up? We could describe something like that. Well, then that would be 3 pi 0. That's the first point in the center of the wave as the graph's on its way up. So this is what it is. It's a game of how do you scale the x-axis. All right, cool. Any questions? All right. Okay, so let's look at generating some equations. So a couple of things when you're trying to generate a wave like this, all right? I gave you guys on Wednesday just sort of the standard format of a wave, and we used capital A, B, and C, and D, okay? One thing you want to make sure you keep in mind is that the letters are arbitrary. And so sometimes when you'll see people give you an equation like this, and this one they use lowercase a and d, but they put them in the same place we called a and d, right? But I've seen problems where they might have c sine of x plus a on the outside, right? So you don't want to just blindly memorize the letters and start using the formulas I gave you. So it is the position in the equation that matters more than the letter. We can change the letters all day long. So if I throw a c in front of sine of x, well then c becomes the amplitude because it's positioned in front of the function, right? Any letter I add or subtract on the inside, right, is the phase shift. So make sure that you don't let yourself get like hung up because you just see a different notation. The letters are completely arbitrary and we can make them up and change them around all day long, right? So then they told you they want you to find A, which is the amplitude, and D is the vertical shift for a wave that oscillates between -3 and 13. So oscillates just means bounce, right? And they've actually given you the range of the wave because that means this wave goes from -3 to 13. So we know the max and we know the min. If we want to find A, well, the amplitude, we said, if you take the maximum, subtract the minimum, that gives you the total height of the wave, and then you cut that in two, that's going to give you the amplitude. So 13 minus 3 divided by 2 is 16 over 2, and we get an amplitude of 8. To get the vertical shift, right, that's the middle line of the wave, and so you just average the top and bottom together, and that gives you the middle. So this time it's 13 plus negative 3 over 2. We get 10 over 2, which is 5. Our final answer, we have to put these values back in the equation. So f of x is 8 sine of x plus 5. Now we can easily check ourselves because we actually know more than one way to do this. So the maximum of the wave should be the middle value plus the amplitude, and 5 plus 8 does in fact give us 13, right? The bottom of the wave should be 5 minus the amplitude, which does in fact give you negative 3. So if you think you've got these formulas backwards, right, and you calculated them in the wrong way, you do have another way to check yourself to make sure that your final answer matches the wave you were given in the equation. All right, so let's look at finding the equation when we're looking at graphs of the waves. So we're going to look at 2 of these. So if I just give you these 2 pictures, but I don't put any context around them, right? Just say, write me an equation that'll generate these graphs. Well, they could be a sine wave or a cosine wave. They're actually 2 correct answers. And furthermore, depending on how you read the phase shift and which wave you pick, there are multiple right equations that would give you these same waves, right? So we're always going to have to narrow it down for you, right? So if these were cosine waves, then the first picture on the left, right, there's no phase shift there because it starts right at the maximum like it should. There's no vertical shift because 0 is the middle. So I can just read the time period, grab the amplitude, and I could write the wave. If you look at the graph on the right, and I tell you it's a cosine wave, well, some of you might read it as, oh, well, they just took a cosine wave and flipped it upside down. So I'll just throw a -1 out front, and that'll let it start at its bottom, right? But some of you could have read it of, oh, they took a cosine wave and shifted it left 2 places, because that's where the peak is, right? Or you could even read it as they shifted a cosine wave right 2 places. So that's what I'm saying. There's lots and lots of interpretations. Don't freak out if we kind of leave it open-ended and you have the freedom to come up with a lot of different waves, right? But for this problem, we're actually told that it's a sine wave, and we need to come up with the equation y equals a sine bx plus c, where a is positive and c is negative shift, okay? So it's not telling you c is a negative number. Now, c is a negative number the way we've learned the equations, but it's saying negative shift. So it says if you think there's a phase shift, assume left shift, right? That it went to the left. Because otherwise, when you're giving your answer to a computer, there could be infinitely many right answers, right? And sometimes we'll say things like the smallest shift, right? C is the smallest value. And what we mean is when you look left, find the first time that that point occurs, right? So for the first wave, we're going to pull the amplitude. So what's the amplitude of the wave? 2. On the second wave, right, it also has an amplitude of 2. On the first wave, right, we have to get the time period. So for this wave, we actually have a couple places you can look, and I recommend that you look in a couple different places just to make sure that always lines up and you're reading it right. So if I read it as peak to peak, well, that's 0 to pi. There's a time period of pi, right? If I read it from trough to trough, well, negative 2 pi to pi over 2, or negative pi over 2, excuse me, to pi over 2 is pi, right? So no matter how you read the time period on this graph, we're getting a time period of pi. On our second graph, same thing, right? I can read it from 0 all the way over here to 4. That would be trough to trough, right? I could read it from negative 2 to 2. So on this graph, we're getting a time period of 4. In my equation, though, I need the frequency. So B is 2 pi over your time period. So over here, I get a B of 2. And over here, 2 pi over 4 becomes pi over 2. So look what happened in these two graphs. If your x-axis is indexed in some version of pi, the pi gets canceled out when you convert it to b, and you just get a constant in the equation. But if the x-axis is indexed by constant numbers with no pi's in them, well, when you convert to b, you're going to have a pi left over in your answer. So that can happen, and it's fine. It's supposed to happen, all right? Now we have to figure out the phase shift. So they want C to be negative shift, and we want the first time it occurs. So on a normal sine wave, the wave crosses the origin, and the wave is on its way up, all right? So if I look to the left of the y-axis, well, there's the first time that point occurs. If I look at my other wave and I go to the left, there is the first time that that point occurs. So C in the first graph is going to be what value? And this is something we're going to do to you. Notice it's not marked, but there's a lot. Yeah, it's pi over 4. So that happens right in the center of that interval, so you just chop it in half. And that's when you use the properties of waves, right? So this is actually negative pi over 4. Over here, the same thing, we would say that that's negative 3. There's no vertical shift on either one of these lines. So now when I write the equation, I recommend that you use the standard form we've been using, and then you just convert it into what they want, right? So on the left over here, we're going to get y equals a, right, times sine of b times x minus pi over 4. And then when you distribute the 2, right, you get the wave in the form that they wanted. So the first line lets us see the phase shift in the equation. The second line, you can't actually see the phase shift. You'd have to factor the 2 back out, right? For the other wave, we have y equals 2 sine of pi over 2 times x minus 3. And now, when I distribute the pi over 2 out, so in this equation, what they're calling lowercase c is not the phase shift. It's actually the frequency times the phase shift. So I would always start with your general equation, and then you just simplify it. Now you've got the form that they wanted. And because we shifted left, right, we got negative c values, and we plugged them in the equation, they turned into positives just like they should have to get our resulting equation. All right, so the last thing that I want to talk about today is domain and range of the remaining 4 trig functions. So the graphs of these functions are on your graphs you should know sheet. So make sure that you're looking over them. But I just want to talk about some characteristics so we can make sure when we're doing problems we're reading them right. So only sine and cosine waves have amplitude. Those are the only ways that we talk about amplitude. But the remaining 4 trig functions, you can absolutely put a coefficient in front of them. It just vertically stretches them, but they don't have amplitude based on the shape of their graph, right? If we're looking at these functions, they are periodic, so they do have periods. And they've got domain and range. So the period of a tan and a cotan wave are the same, right? Just like sine and cosine have the same period. But the remaining 4 trig functions are all fractions. So if you have a denominator, then you're going to have issues with 0 in the denominator. So what is tangent in terms of sine and cosine? How do you rewrite tan in terms of sine and cosine? Anyone remembers? It's sine over cosine, right? So anywhere that cosine has a value of 0, tangent can't exist. So if you look at the graph of tan and cotan, you see vertical asymptotes. Those vertical asymptotes on a tan graph occur everywhere cosine is 0. So cosine is 0 on the unit circle at every odd multiple of pi over 2. So at pi over 2 at 0, 3 pi over 2, we kept going 5 pi over 2, 7 pi over 2, 9 pi over 2, same thing in the negative direction, negative pi over 2, negative 3 pi over 2. So those values are happening every pi. So the tangent wave, right, and cotangent, they're not really waves, right, have to repeat every pi because that's when the zeros, sorry, I'll move that down there a little bit. That's when the zeros occur in their denominator. So that's why it's got half the period of a sine or cosine wave. So then that means we're going to have an issue with the domain. So for tangent, the domain doesn't exist, or let's put it this way, all values are kicked out of the domain wherever cosine is 0, right? And that's at those odd multiples of pi over 2. So one of the ways we describe the domain of tangent x is all reals except n pi over 2, where n is odd. If you tried to write an interval notation, we'd have to give you a starting and stopping point because there's infinitely many intervals. So if you wrote an interval notation, you would have to say, well, negative pi over 2 to pi over 2, union, pi over 2 to 3 pi over 2, union, right? 3 pi over 2 to union, and that would take forever. So this is an alternative way. We just say everything but these guys, right? The range is all reals. So tangent graphs go from negative infinity to positive infinity. They just chop up over that, right? So for cotangent, that's cosine over sine. So the asymptotes on a cotangent graph are going to be everywhere sine is 0. And sine is 0 at 0, pi, 2 pi, 3 pi. So the whole number increments. And so what we say there is all reals except n pi, where n is an integer. So now that gives us 1, 2, 3, 4, 5, 6 pi, but it also includes negative 1, negative 2, negative 3. So it's kicking out all the appropriate places, and the range of this is also negative pi, or negative infinity to positive infinity, right? So the last two are, how do you deal with cosecant and secant? So cosecant is 1 over sine, right? And secant is 1 over cosine. So their graphs are linked, okay? So that means if sine repeats every 2 pi, then cosecant has to repeat every 2 pi, and vice versa with secant and cosine. So the periods of these waves, right, line up with their waves that they're existing on. So the way these graphs work, right, you're going to have a bunch of vertical asymptotes because if cosecant is 1 over sine, anywhere sine is 0 is going to give you a problem, right? So the domain of cosecant is actually the same as cotangent because it's sine in the denominator creating your issues. So we actually know without even looking at the graph that all real numbers except n pi, where n is an integer, because that's rule number 1 for domains, no zeros in the denominator, right? And so that also means on a secant graph, right, it's all reals except the places that cosine is 0, and those are the odd multiples of pi over 2. So the way that secant and cosecant work is they kind of look like teeth, where every other tooth is missing, right, the top and bottom. And if you draw a sine wave, a cosecant wave touches it on the top and bottom of all of its troughs and crests. And they actually touch at exactly 1 point. So, and then they go up to positive or negative infinity depending on what side of the graph they're on. So for both of these guys, they have the same range. They go from negative infinity to the bottom of their respective waves, right? Which, so that's -1. Then it picks back up at the top of the wave and goes to positive infinity. And so if you actually look at them, they look like teeth. And if you look at them side by side, it just looks like the holes in this mouth are filled in by the holes in this mouth. And that has to do with the asymptote shifting because it's sine or cosine causing you the problem in the denominator. So these ideas are all linked, and this is what I was saying earlier. If you really know how sine and cosine work, you can decipher all kinds of things out of the other 4 functions, because anything that stops sine is going to get in cosecant's way, right, or cotangent's way, and then anything that stops cosine is going to get in secant's way or tangent's way. All right, so that's all I have for today.